Okay, maybe we can start now. So, welcome everyone to Bosonic Learning Winter School. It's a real pleasure to introduce Marco Fanizza today. So Marco is currently researcher in INRIA, Paris, and his work is in quantum information theory with focus on quantum statistical inference and also for quantum communication in both discrete and continuous variable settings. Okay, today he'll giving a lecture titled Hamiltonian Learning for Bosonic Gaussian State, and please welcome.
Thank you, Lucio, for the very nice introduction. Yes, so I will tell you about this joint work with Cambi Ruse and Daniel Stilk-Franza on Hamiltonian structure, trace distance learning of Gaussian states. And yeah, so in this work, we want to learn the Hamiltonian of a continuous variable system of m modes, finite number of modes, given n copies of the corresponding Gibbs state, just this expression. And this model represents access to copies of thermal equilibrium states, encoding the dynamics, so that via the measurements and their statistics on this, collecting statistics of measurements on these states, we can reconstruct the dynamics of the unknown system. So in particular, we focus on the case where interactions are local, which is typical in many body physics. And in this case, the structure of the Hamiltonian can be described by an interaction graph with m vertices. Each vertex corresponds to a local subsystem of the many-body system. And E edges, set of edges that connects two vertices if there is an interaction term connecting those two vertices in the Hamiltonian. And we want to limit the degree of locality, which is measured by the degree of the graph, where the degree of a vertex is the number of edges attached to the vertex, and the degree of the graph is the maximum of the degrees of the vertices. So in this case, we will denote the degree as delta minus 1. In our work, we do an even further restriction. We are considering Hamiltonian of CV systems, but in particular quadratic Hamiltonian, in the sense that these are operators that are quadratic in the position of momentum of operators, which can be collected by these vectors of operator R. And the Gibbs states corresponding to those Hamiltonian are Gaussian states. And in fact, every non-degenerate Gaussian state is a Gibbs state of a quadratic Hamiltonian. So in particular, the beta, which is the inverse temperature, and it's a scalar, times the Hamiltonian operator can be written in this formula, using this formula, where TIs are multiples of the identity operators times, in this case, these are the first moments of the state. And RIs are exactly coordinates of this vector of operators. And our interest is mostly in determining Hij, which is a matrix, a real matrix. So it's not an operator in the infinite dimensional system. This is a matrix of 2m times 2m real numbers. It's symmetric and it's positive definite. And the graph and the sparsity of this Hamiltonian can be represented through a graph. So in particular, this would be an example of such Hamiltonian. So the picture here would be an example of a sparsity structure for such an Hamiltonian, where each mode of the system is associated to a pair of position and momentum operators. And each block on the diagonal, 2 by 2 block on the diagonal, is associated to a mode of the system. And for the off-diagonal block, the ones that are colored in red are those where there is at least one. Sorry, I just recovered from a flu. So those of the off-diagonal that are colored in red are those where there is at least one matrix element that is non-zero. So there is an interaction between two modes if the 2 by 2 block corresponding to the pair is non-zero. And if you order the vertices in this graph from left to right, then you see that the edges of the graph correspond to colored 2 by 2 blocks in this matrix. And the ones that are not colored are just zero. So this is quite important for what it will follow. So if you have questions now, I will be happy to answer them. Okay, so I assume it's clear what the Hamiltonian matrix is. I see something in the chat. Okay, so this is a case where we do Hamiltonian learning with the Gibbs state model. And there is a real-time evolution Hamiltonian learning model in CV system. I will mention, yes, at least one work that does it. But if you want, I can give you references for this. But yeah, in this case, we'll only work with the Gibbs state model. Okay. Yeah, so let me also talk about the previous work for learning in the Gibbs state model for the discrete variable case. So this has been a quite important topic recently. And there has been recent work on computational and sample efficient algorithms when the graph is known. But in general, there is still no efficient graph learning algorithm. So before we put our work on the archive, the best results gave polynomial sample complexity in the sample complexity polynomial in the system size and similar computational complexity. And then later, actually, it was also proven that it is possible to learn with the logarithmic number of copies for general graph and with a more refined sample complexity in terms of the other parameters that I report here for lattices. But anyway, this is still far from the efficiency for these problems in the classical version of the question, which is learning classical random Markov fields over Gaussian graphical models in the continuous variable setting. In this case, log m over epsilon square copies are sufficient for both Hamiltonian and graph learning. So we wanted to try to fill this gap, and in particular go into the direction of the CV case, because in particular the Gaussian states behave in certain ways semi-classically, and so we hoped it was possible to leverage the intuition from the classical algorithm to give a good algorithm for a genuinely quantum problem, and that's in fact what we were able to do in this work. And I would also, yeah, perhaps by now you have been convinced by of this via these lectures, but it's very, yeah, learning with continuous variable systems is a an area that is rapidly developing, and it's important because there are many systems that can be described by CV Hamiltonian, and in particular quadratic ones, such as electromagnetic fields, optomechanical systems, trapped ions, cold atoms in optical lattices. And also, there are today analog simulators of lattice bosonic Hamiltonians where one can engineer these interesting local Hamiltonians with different kind of geometries. For example, using magnetization fields from cloud of rubidium atoms, which was used to construct Hamiltonians on 18 sites or 18 modes, using superconducting optomechanical systems, and also photonic synthetic lattices can be realized. So this motivates considering the problem, especially of Hamiltonian learning in the CV case. I can mention now just recall the recent results in quantum continuous variable learning that have appeared really recently, such as general trace distance learning, results Gaussian trace distance learning and Gaussian trace distance bounds, Gaussian testing, Gaussian unitary learning, and also, yes, Hamiltonian learning for time evolution, for example, exactly. So I have two references here that, as someone asked before. By Li Tong, Gefenini, and Ying, and Mobius Bloom, Caro, Vernon, and Jose. Okay, so now let me state what our results are. So we are able to establish the following. So with this work appeared the first result on the sample optimal scaling imprecision for trace distance, that is the 1 over epsilon square. It's valid for, in this case, for mixed states. We have to assume that the state is mixed to make this work. More importantly, our core results are efficient Gaussian Hamiltonian learning when the graph is known, and efficient graph learning. And in both cases, for bounded degree, we show that if the degree is constant, does not depend on M, we show that the number of copies that we need is logarithmic in M. And the dependence on the precision in Hamiltonian learning is 1 over epsilon square plus a correction. So in the original version of this work that is still on archive, we had specific functions of the degree here, but actually we refined the analysis and we will update the paper to show that in fact this correction in the exponent goes to 0 when epsilon is small. And this is, so there is this formula for general lattices, for general graphs, and for lattices we can improve it to this formula, to this dependence on epsilon. And then we can also do a graph learning with a similar sample complexity, where kappa now is a threshold parameter that we use to tell if an edge is there or not. And the measurements that we do in this algorithm are just heterodyne measurements, so non-entangled. And then we use classical post-processing. The total computational complexity is polynomial in the number of modes and copies for Hamiltonian learning, with a degree that does not depend on the other parameters. While for the graph learning instead, we still get polynomial in polynomial sample complexity, polynomial computational complexity in number of modes, but the degree depends on the other parameters. In these results, I suppressed the dependence on the norm of the Hamiltonian and on the norm of the inverse. These are assumed to be uniformly bounded. And I invite you to see the paper for the details. But however, trying to improve the dependence on this parameter is an important open question. So now I'd like to tell you something about the ideas behind the proofs of this result. And so, as I said, the inspiration comes from the classical case. And there is a formal parallel between classical Gaussian distribution and quantum Gaussian states. So what we call the Hamiltonian in the quantum case is often called written as theta in the classical literature and called the precision matrix. The covariance matrix in the classical case is defined as the matrix of the second moments, and this is the analog of the quantum covariance matrix, which is obtained from the anti-commutator. And in the classical case, the relation between the precision matrix and the covariance matrix is very simple. Theta is just the inverse of 2 times sigma. In the quantum case, the relation is more complicated. It involves the matrix of the commutation relations, and it's what's written here. What's nice is that the relation is still one-to-one. So this suggests that if we can estimate the covariance matrix, we can also get an estimate of the Hamiltonian using this formula. And of course, there is a naive way, which is doing a plug-in estimate. Just plug an estimate of the covariance matrix in this formula and then get an estimate of H. But this may be not the smartest choice, and that's what our paper is about. Anyway, having an explicit formula also allows to do matrix perturbation theory to understand what error we accumulate on what error propagates to H from an error in the estimate of the covariance matrix. I would like to tell you how precision matrix learning works in the classical case. So of course, as we said, you can get the precision matrix by inverting the covariance matrix. So a natural way to estimate the error on the precision matrix is just to use this simple linear algebra relation between the difference of the inverses and the differences of the original matrices, which using submultiplicativity of operator norm gives this inequality that allows one to bound the error on the operator norm error on theta in terms of the operator norm error on sigma. However, yeah, this is not the smartest thing to do, and one can do better by using the sparsity assumption. So let's now just consider an Hamiltonian sorry, this should be actually theta if we stay in the classical case. Let's consider let me call it Hamiltonian. I think it would be easier. Hamiltonian, which is delta sparse. That means that there are at most delta non-zero elements on each row and column. And this means that there is a specific structure of conditional independence in the probability distribution of the associated normal random variable, multivariate normal. And what is interesting is that if we take the marginal over vertices 1, 3, 7, here note that Vertex 1 is the first on the left, and it's connected to vertex 3 and 7 only. So if we take the marginal corresponding to the neighborhood of vertex 1, we can compute this by integrating out the other variables. And it turns out that the Hamiltonian of the resulting density has the same first row and first column of the original one. And this means that if you want to understand the interaction of vertex 1 with its neighbors, it is sufficient to get access to the covariance matrix of the neighborhoods of vertex 1. Because by inverting it and reading the first row and first column, you can just read the true entries of the full Hamiltonian. Let me again repeat this graphically. So if you look at the covariance matrix of vertices 1, 3, and 7, and you invert it, and you look at the first row and the first column, if you have them exactly, then these are really corresponding to the first row of the full matrix H and the first column of the full matrix H. And if you have errors this on the initial V, then okay, we will have you have learned anyway the matrix elements of the full H with some error. This is a very important point, so if there are questions on this, please let me know. Okay, so I would also like to say that we had an explanation for this phenomenon, just looking at the density and how it behaves under marginalization. But actually, we know that we have formulas for that relates covariance matrix to precision matrix or Hamiltonians, and so we could have just used those to observe this fact, that is that entries of the Hamiltonian can be recovered by local inversions of covariance matrices. And the reason, the linear algebraic reason for this is the Schur's complement. So in particular, if you have a matrix that has 4 blocks A, B, C, D, and you write the inverse, then the upper left block will be the inverse of A minus B, D minus 1, C. And if M has the right sparsity structure, that means that the first row of B and the first column of C are 0, then again, if you do the inverse of n minus 1, this will have a first row and first column which are equal to the first row and first column of A. Okay, so this is perhaps a bit too much to absorb quickly, but what I want to stress is that while we won't have the marginalization arguments available in the quantum case, what will be available is that we will be able to invert you will be able to invert a matrix whose inverse is approximately sparse, and therefore we can construct a perturbation of this Schur complement argument to learn the global matrix accurately. Okay, so let me also tell you something about why local inversions are more effective than global ones. So first of all, the covariance matrix has 2m times 2m elements, and so to learn them at precision epsilon, just by using union bound, you can do it with 1 over epsilon square log m copies. But then to get to invert this, you have to evaluate the operator norm error of the matrix. And this, if you try to do it with the full covariance matrix, will give you a blow up, which is linear in the number of modes. And if you use the matrix perturbation bound for the inverse that I showed you before, this incurs again in a linear upper bound in M, which would defeat, which would obstaculate you to get a logarithmic in M sample complexity. This would be impossible with this kind of error. On the other hand, if you only invert local matrices, this will have size at most delta, which is given by the degree of the graph. And therefore, the operator norm error will be bounded by by something that goes like delta times epsilon. And and then the entry-wise error for the Hamiltonian matrix will also scale with delta rather than with M, and this will not spoil the logarithmic, the dependence, which is logarithmic in the number of modes. So we want to promote these ideas to the quantum setting. But first of all, let me also mention that in the classical case, there are a lot of very nice algorithms to do this. And in fact, when the graph is known, the problem is a bit easier. So most algorithms directly work in the situation where the graph is not known and you just assume sparsity. And here I can mention the graphical lasso and other approaches such as the lasso, Danzig, or climb, which are also efficient on the computational side, but they are sensitive to the condition number of the precision matrix. But recently there has been a paper that shows a sample complexity that does not depend on the condition number, and this is for graph learning, which matches information theoretic lower bounds, but the trade-off is a worse scaling in computational complexity. This is to convince you that there is a very wide, a very nice literature in the classical case, and while this work is the first that addresses this problem in the quantum case, and there is still a lot to do to get to the level of depth that of the classical literature. Okay, so the core of our algorithms is to understand how to treat this relation between Hamiltonian and covariance matrix. So I gave you before a compact formula, but actually the one that we think that we use is another formula that uses an integral representation of the logarithm, because in this way we can express everything in terms of 2v minus I omega inverse. And so our strategy would be to first learn a good estimate of 2v minus I omega inverse, and then plug that matrix in this formula, and then just use triangle inequalities and the usual matrix perturbation bounds to get an error over H. And the reason why we do this is that 2v minus I omega inverse is approximately sparse and and we can learn it efficiently in a way that does not depend on the number, so it does not scale polynomially with the number of modes. Let me also mention our result on trace distance learning, which comes from a very, what I think is a very nice observation. Here again, we use heterodyne to get an estimate of the covariance matrix. And then to bound the trace distance, we use Pinskers inequality in a symmetrized way, so that we take the sum of the relative entropies of rho and rho hat in exchange order. And this simplifies for non-zero mean states in this way. It's slightly different from if there is the state are non-zero mean, but it doesn't matter for this computation. For at least to get this kind of result. And so in this case, you see that if you have v minus v hat that's precise at order epsilon, and also h hat is precise at order epsilon because of our continuity bounds, then again the the trace distance is bounded by a linear function of epsilon. A previous bound were just square root of epsilon, and at the same time as this work appeared, there was also another work that showed this linear bounds in epsilon for the full set of Gaussian state. In our case, we have to restrict to mixed states, otherwise we risk these relative entropies to be divergent. And this is the full statement where, yes, the novelty is mainly in the 1 over epsilon square. But we can give a detailed dependence on parameters of the Gaussian states, such as the norm of the symplectic that appears in the Williamson form, and the norm of, and the maximum and the minimum symplectic eigenvalues. Okay, so let's go back to Hamiltonian learning. As I said, 2v minus I omega inverse is approximately sparse. One can write an exact formula for it, and then use the Taylor expansion for the exponential to write it as a first term which has powers of h up to L. That means that it can only populate matrix entries that are at distance L from the original nodes. And so that the sparsity would be at most delta to the L. And the error term E decrease faster than exponential intruncation degree. And using again the Williamson normal form, it's possible to see that by choosing L that goes like log 1 over epsilon over log 1 over epsilon, the operator norm of V is of order epsilon. And so 2v minus I omega inverse is approximately sparse, and we can run a perturbation of the Schur's complement argument to learn it. So now, instead of having neighborhoods of radius 1, really just looking at the first neighbors to each mode, we have to enlarge our window to neighborhoods of radius that depend on epsilon, as I showed before. And then what we do is what we called quantum local inversion. So we look at the estimates of 2v hat minus I omega for the neighborhood of the vertex I. We invert it, and then we look at the first two rows and the first two columns, and we use them to populate our estimate of the global inverse of 2v minus I omega, which we are indicating as Li, meaning local inverse. And it turns out that that the global error in operator norm has two main contributions, one that comes from the truncation error and one that comes from the statistical error. And one has to check the trade-off between these two, because if big L means that E is small, but on the other hand, it also means that we will have to do local inversion, which use larger matrices, and so they contribute with this kind of error, and yeah, that increases if the matrices to invert are too large, become larger. But it's possible to find a good value of L such that everything is under control. And then once we have a good estimate of 2v minus I omega inverse, we can just plug this estimate in the formula for H. And this gives our Hamiltonian estimate. In fact, this is what we can take as L. This W here is a Lambert function. Again, these results are still not available on the archive version, but yeah, we will update it soon. And we also recently did some numerics that show that our methods, in fact, works in interesting regimes. We tried with well-conditioned Hamiltonian, where both the operator norm of the Hamiltonians and of its inverse are independent on the size, which is the setting where our theorem give guarantees. And we see that global reconstruction using the plugin method does significantly worse than the local reconstruction. And interestingly, this is also true for real conditioned Hamiltonians, where our theorems are not really conclusive. And so this gives us the hope that, in fact, we can improve our analysis to treat this case too. This is for a very simple graph. I have to say it's just on a line, but yeah, it will be interesting to see how this algorithm performs on more complicated graphs. And finally, let me also tell you something about graph learning. So here we start with a promise. The promise is the following. We say that all the edges are such that there is at least one entries of the 2x2 block associated to the edge that is larger than the threshold kappa. And the algorithm works as follows in a kind of brute force search. There is an iteration over all possible candidate neighborhoods and adversarial neighborhoods of radius L. So the size will be delta to the L if we don't know the graph. And L has to be tuned. And then for each choice of an I and adversarial neighborhoods, one does a local inversion with the union of the two neighborhoods. And if in the inverse there are never large entries on the blocks that do not correspond to the candidate neighborhood, then we accept an I. So we have to run this for every adversarial neighborhoods. If it passes the test for all of them, then we accept the candidate neighborhoods. And then we will compute the local inverse with the candidate neighborhoods and thus an estimate of the Hamiltonian. And finally, we will remove spurious edges, the ones that are below threshold. And the reason why the algorithm works is that if the candidate neighborhood is correct, then the entries of the local inverse of on an I union the adversarial neighborhood are accurate, and so the entries that are outside the candidate neighborhoods are small, and we will correctly accept an I. While if an I is not correct, then if there will be a completing neighborhood, adversarial one, such that the union is contains a good neighborhood, and now we will have accurate estimates for the entries that are that are in an I but not in that are in the adversarial one but not in in the original one, and this will be we will correctly accept an I if all the missed entries are small, because then we check that they will not play a big role in the error computation, or we will correctly reject an I if we missed a big entries that it's revealed by this correct estimate in this step. And so with the accepted neighborhood, we obtain a good estimate of the Hamiltonian, and this also allows to find a good graph to select the correct edges. And this with a logarithmic scaling in the number of modes, because we only need to invert locally at each step. And again, this is the statement of the result. Yeah, we have a graph of bounded degree, edge set E, a certain condition on the entries of the Hamiltonian that need to be to respect this threshold. And then yes, so with the number of copies that is logarithmic in M and depends in this way on the threshold, then we can learn the graph. Again, I'm suppressing the dependence on the other parameters. This is in fact quite important. We have to assume them to be constant with respect to M, and anyway, it will be important to make this dependence to improve this dependence for a final statement of this kind. Okay, so I can conclude now. In this work, we have found sample complexity upper bounds for Hamiltonian learning for bosonic Gaussian states. We have efficient learning algorithms with practical measurement schemes, heterodyne. In particular, we also showed optimal scaling in precision for trace distance estimation. And and most interestingly, there are many important future directions to pursue, including lower bounds that use sparsity structure to get a specific answer to this problem of Hamiltonian learning. As I said, improve the dependence on the other parameters, epsilon, delta, norm of H, norm of the inverse of H. Also, in the classical case, there are papers that deal with graph learning with relative strength promise rather than this additive threshold, and that would be very interesting to do also in the quantum case. And it should be also possible to adapt these techniques to study the fermionic case. And in fact, it's probably easier than the bosonic case. So that's also a very natural question to look at. And with that, I thank you for your attention. And I take question.
Yes, thank you very much for that lecture. And is there any questions from audience here?
Can I do a question?
Mhm.
Um, um, Thank you for your great lecture and the idea about the inverse of sparse matrix. Um, um, is there any idea for to reach the lower bound of this Hamiltonian learning complexity?
So is your question if is there are ideas to write lower bounds or to attain lower bounds with the corresponding upper bounds? I'm not sure about the question, but anyway, I haven't seen a specific lower bounds for the quantum case in Hamiltonian learning. There is a classical paper about lower bounds by Wang et al. And the techniques should be generalizable to the quantum case. It should be doable. It doesn't seem difficult, but it would require a little bit of tweaking. In terms of reaching it with an algorithm, I don't know because um, yeah, it's I still we have to see what is the lower bound, and then it's complicated to understand what are the best algorithm. For example, this algorithm uses unentangled measurements, and I wonder if these problems are just can be solved just by unentangled measurement, or entangled measurement can give a boost to the performance. It's still unclear. But anyway, one thing that I would really care about would be to simplify the dependence on the condition number of the Hamiltonian. That's really something that bugs me, and I think it should be possible to um, yeah, reduce it by a large degree. Yeah, if you're interested, we can talk. If you want to try and to find lower bounds, I'm available to chat about it.
Great. So other questions here? Maybe I have small questions. So
Mhm.
is it natural if these ideas can be used to learn the parameters and structure of local Gaussian channels or?
Okay. Which model of local Gaussian channels are you thinking about? There could be several models. Like you could have I don't know, Gaussian Lindbladians. You could have networks of Gaussian channels. You can implement the locality in several ways, and it's a very interesting direction. And I don't know. Probably, yeah. I haven't thought about it really. I think yes, there should be something along these lines also for those cases.
Other questions here? Oh, I think one question in the chat box.
Mhm. Aha, okay. Uh, yeah, we are trying to understand that. No, but yeah, it's I don't have any answer at the moment. So the question is it known? So the question, I guess, it's so qubit system Gibbs states are efficiently learnable in high temperature, low beta, and known that they are locally Markovian. I'm curious the specific case. Is there a separation on beta or anything know about local Markovian? No, these are very, very good questions. I am also starting reading the literature on this, so I'm not sure I can say that I am fully up to date, but I don't think this is resolved. So when you say they're efficiently learnable in high temperature, yes, yeah, I think I get which paper are you referring to. Um, No, well, for general, so of course, our paper gives you an answer for Gaussian states, for quadratic Hamiltonians. You could, I think you could look at what we have, and apart from this condition number problem, yeah, then they are efficiently learnable at any temperature, in fact. For general Hamiltonians, I think we don't know. And one problem that we could have is the fact that it's not true now in infinite dimensional system that sending beta to zero recovers the maximally mixed state, right? So yeah, that's an important difference. Yes, yes. Let me, yeah, drop me an email.
Great. I think we have time to one more question. So the dependence seems to be on the order of 1 over epsilon squared, right? So is it
Okay, so yeah, it's to be fair, it's 1 over epsilon. So this gamma here depends on all the other parameters. Yeah, for example, yeah, this gamma depends all on it's a complicated function of the other parameters, which goes to zero when epsilon goes to zero, but it goes to zero very slowly. It's like 1 over log 1 over epsilon. So yeah, I wouldn't say it's practically epsilon square. It's
oh,
just that if epsilon becomes very, very small, then it is effectively epsilon square.
mhm,
But if it stays at a reasonable size, then you will have a different
mhm.
correction here. Yeah.
So is that barrier come from Taylor expansion type argument or can be improved using other techniques?
Mm, let me think about it. Yeah, exactly. I think it's yeah, it comes from there. It comes from the specific type of bond you can put on the truncation of the Taylor
Mhm,
expo of the yeah of the exponential Taylor series of the exponential. And yes, I would be very interested in finding other ways of 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 uh, of learning the Hamiltonian that do not pass through this
mhm,
uh, system. But okay, so for lattices, so for more in general, if the neighborhood size of the neighborhoods grow power law rather than exponential. So for a general graph with degree delta, then the number of sides that are at distance L grows like delta to the L. But if for lattices, this will grow like L to some power, no? So in that case, we can show that it's 1 over epsilon squared times a polylog in 1 over epsilon. So yeah, at least in that case, it's more under control.
great. Great. Thank you for all the nice answers, and maybe we can finish this lecture today. And yeah, thank you again very
Thank
much
you
for
very
the next
much.
lecture. Yeah.
Pleasure.
Okay.
Goodbye.
Goodbye and have a nice day.